Welcome to the Components of Internet of Things course.
Welcome to this session on data sensing for an IoT networks, where I will explain the data sensing methods through smart kits such as biomedical signal plugs, which is for biomedical monitoring, smart health for e-health monitoring, smart city for different type of sensor required for a smart network in a city, and smart agriculture, where I will be showing you the sensors related to the agriculture. As we all know, for an IoT network, the most important thing is the things. The things in any IoT network is the sensors. So to start with, what is a sensor? As we know, sensor transform energy from physical domain into electrical domain. A very basic and popular example is a thermocouple, where the temperature is recorded and the heat energy of the temperature is further displayed using electrical measurement, and you see the electrical measurement of the temperature. Another very popular example of a sensor is an accelerometer, which converts your linear motion into digital values, that is from linear motion to electrical conversion. Now, there are three very popular terms in things in IoT, which are sensor, actuator and transducer. So as I discussed, sensor means which transform energy from physical, that is non-electrical domain to electrical domain, and actuators transform energy from a physical non-mechanical domain to a mechanical domain. People often confuse with these two terms. A very popular example for an actuator is a micro mirror. Now, what is a transducer? So transducer is a combination of both sensor and actuator, where they both are used to transform signal or power from one domain to another domain. A very popular example for a transducer is a microphone and a loudspeaker. As you know, in loudspeaker, our voice energy is further converted into electrical energy and amplified. So these are three very important terms when you talk about sensing in an IoT. Moving ahead, so how does sensor basically measure the data? It is very important to understand the architecture of a sensor node. So at the heart of the sensor we have a microcontroller. We have, in current times we use smart systems such as Raspberry Pi as a microcontroller for sensing the devices. So any sensor will have at its heart a microcontroller, and it will have a sensing unit. That sensing unit will record the data and convert it from the analog form to the digital form using an ADC converter. This ADC converters interacts parallelly with the microcontroller. This microcontroller is always connected with a battery or any electrical source, and it also has some external memory. Hence, any sensor device, whether it is for any field such as biomedical or smart health or smart city, will comprise of these four basic units, that is a microcontroller, an ADC, a battery, a transceiver and an external memory. The transceiver for a sensor is very important, because once a sensor sends the data, it not only receives it, it also has to transmit it to a cloud or to a microcontroller or to a base station or to a system. Hence, transceiver play a very role in any of the sensing node architecture. Now, moving ahead with our tutorial for biosignal plugs, which is a medical sensor kit. So in this wearable biosensing kit, we have 8 type of sensors. Now, these 8 category falls into number 1, electromyography, the EMG sensors. EMG sensors are used to assess the health of the muscles. How do the muscle contract? How do the muscle relax? What are the movements? In which direction is the movement? These all sensing is done through EMG sensors, which is electromyography. Another type of sensor in this biomedical kit which we have in our lab is EEG, that is electroencephalography. To measure the signals which are coming out of the brain, we need sensors. These signals are of very small values in microvolts. So we need very highly sensitive sensing devices which can amplify the signals and measure the value. For that we use EEG signals which are deployed on the brain to measure the signal. Third type of sensor which is in this biosignal plugs kit is ECG, that is an electrocardiogram. An electrocardiogram comprises of sensors that measure the signals coming from your heart. So when a heart contracts and expands, a small amount of current flows through the fibers, the pungent fibers which are in the heart. That particular signals are measured by these ECG signals, and they display the waves which are popularly known as PQRS waves. Hence, by doing some analytical methods on those signals, we can identify the condition of the heart of any person, whether he is normal, abnormal, or he has a particular type of arrhythmia. Another very important type of sensor is an accelerometer. An accelerometer basically measures the movement of a particular device or a human in a particular direction, that is x-axis, y-axis and z-axis. So in this kit we have accelerometer which helps us in identifying the activity of a person. Now it is very important to assess elderly people or small infant babies through remote sensing or through the remote operations. In that case, if we have signals which are from the accelerometer, they help us a lot in identifying the particular activity which an elderly person or small infants are doing. Then we have another type of sensor which is electrodermal activity sensor, that is EDA sensor, which basically is related to the skin. It basically measures the changes in the electrical property of the skin. That when the skin also produces a certain type of signals which is measured by this sensor for particular conditions, such as whether it's a normal skin, it's a itchy skin, or you are getting any type of shock also, then the skin response changes. So these type of activities are basically monitored by electrodermal activity sensor. Then a very popular sensor which is the temperature sensor. It is self-explanatory. It measures the temperature of any human body or the room temperature or wherever this biomedical device is. Then we have the seventh sensor, which is the respiration sensor. This sensor we apply at the nose, at the nozzle to monitor the nozzle activity of a person. This measures the breathing rate. It is very important for the people who are suffering from asthma or any of the bronchial diseases. There, this respiratory sensor gives a very clear picture whether this person is having which type of disease. And at last, we have force response sensor, that is the FSR, which measures the amount of force any human body or any human body part is exerting on that particular sensor. This in particular is very useful for the people who are suffering from the paralysis or the neuro diseases. when they have what amount of numbness they have in their hand, that can be digitally recorded using FSR sensors. So this biomedical signal flux kit, which comes in this form, has 8 types of sensors as I discussed. Now moving ahead, I would like to explain some of the sensors and how do we record data using this biosignal flux kit. So to show one of the sensors, this is a force response measurement sensor where we can identify the amount of force a particular human part or human body is exerting. So we use our thumb or maybe limbs, and we put pressure on this thin film strip which measures the amount of force which is exerting on the particular sensor. So this sensor can be deployed in a biomedical signal flux environment, which at its heart has a microcontroller. As I discussed, any sensor node will consist of a microcontroller, and our biosignal flux kit also has this microcontroller. This microcontroller has 8 channels in which we can deploy the 8 sensors. Also, at one time we can measure 4 to 5 sensing data from any human body activity. Now, as discussed before, this microcontroller consists of a transceiver. That is, when the sensors are used or deployed in using this microcontroller, it not only receives the data, but it has also to transmit it to a third-party system, which can be a computer, which can be a laptop, which can be a mobile device. So this particular microcontroller that resides in the biosignal flux kit comprises of Bluetooth communication protocol. The Bluetooth 2.0 protocol is used to communicate from biosignal flux microcontroller to the other devices. Now, to give you an example, first, how do we record the data through biosignal flux? Let us say we want to record the ECG of a person. Hence, to measure any ECG activity, we need basically 3 nodes: a positive, a negative, and a neutral node. Now these 3 sensors are used for measuring the ECG using surface detectors, which are nothing but the gels which are deployed on the human body where the heart is located, and then using our biosignal flux kit microcontroller we can measure the waves and transmit it to the third party person. Now to show you, any ECG wave, as I told, comprises of the waveform called PQRSNT, and based on this wave any automated system analyzes the heart activity of any person. So as I told you, we have to deploy this ECG sensor at 3 locations, that is a positive, a negative, and a neutral location. Hence these 3 nodes will be applied to the body part, or basically on the chest of the person at these 3 places. Then we have to connect this ECG node to the microcontroller of the biosignal flux. Hence, for example, if I connect this ECG node to the channel 1 of the biosignal flux kit like this, and then I have to turn on this Bluetooth device. Now since it is blinking, this means now it is ready to record the data as well as transmit the data. And as I told, for any microcontroller it requires a battery or an external device. This kit also has a battery inbuilt in this. So just to first explain you the operation, we deploy this particular sensor at a particular channel, and then we select the right port. We have to select this particular channel port to display the ECG signal. This is done through a third-party software which is called OpenSignal. It is an open source platform which you can easily download from its website, from the internet, and install it very easily on any of the Windows system, or use it as an application also in your mobile phone. So once the OpenSignal detects the Bluetooth of the microcontroller, it shows you a UI like this, and then by selecting the right channel of the microcontroller and selecting the right sampling rate. Sampling rate is number of samples per second your sensor can measure. So for ECG case, we can select 600 Hz sampling, that is in 1 second 600 samples can be recorded, and the resolution of the display will be the 16-bit. Once we select these particular values on the OpenSignal platform, we will get the ECG waves like this, which is very similar to your P, Q, R and S waves. So this is one of the examples through which we can measure the ECG signals. Now, to give you the demo, I will use an FSR sensor to show how this kit records the data and it is displayed on the device. So first, I will use this FSR sensor and I will insert this in the channel 1, and then I will start the kit. See, it is blinking, that means it has started. Then I will go to the OpenSignal platform which is installed in the system. Now, as discussed, to demonstrate how to record using the MySignal Open Kit, as I had shown you before, this is the microcontroller that is blinking, and this is our FSR sensor. Now, in the system which is Bluetooth enabled, when I open the OpenSignal platform, the UI is like this. The first step is to connect it to the system. For that, we have to find out the devices. So when we click on find and configure the devices, it shows one device found, which is nothing but the OpenSignal Bluetooth device, and we can verify this with the MAC address which is given here. So we have to enable this device, and as I told you before, it is configured on the channel 1, hence we will enable the custom channel 1. We'll use a sampling rate of 700 Hz, which we'll select from here, and we'll enable the device. And then once the device is enabled, we will monitor it using the file viewer which will come once the device gets enabled. So trying this, we are first configuring our system. So we can see it is trying to search the device. It clearly shows one device found and the connection is established. initially all the channels are selected, so we will deselect the other channels. And we will start the recording. So this is the window of the file viewer. Now you can see there is nothing on the screen because there is no signal from the sensor. Now as I push the sensor, as I exert the force on the sensor, you can see the waveform changing. Now depending on the force applied, the values are being recorded. If I apply more force, you can see a bigger waveform coming. And if I reduce the force, you can see the values are changing. So this depends on the sensitivity of the sensor also. So here we can see when we are not applying any force, you can see a blank on the file viewer. The moment you apply the pressure, you can record the force. Now, once it is recorded, a very important task for any biomedical analysis is to save the data in the right form. So this tool allows you to save the file in 3 different formats, which are .txt, .h5 and .edf, European data format. Hence, we can save this file on our system as well as on the cloud. For the cloud, you might have to get the access or you have to purchase the storage. But for the file to just store on your system, you have to just click the Save As button and it will ask the name and the file gets saved. So this is how I demonstrated the force response sensor, that it measures the value through the OpenSignal Plus open platform and the BioSignal Plus kit. So moving ahead with another sensor that I described before is the accelerometer. So it measures the acceleration in the 3 axes, that is X, Y and Z. So this is an accelerometer sensor, and since we have 3 axes, so I have deployed it on channel 1, channel 2 and channel 3. Now to enable this, I have to enable the 3 channels on my software also, that is the OpenSignal software, and then only the communication will be set up between the microcontroller and the device using the Bluetooth. So I have enabled 3 channels here, and the file viewer clearly shows the 3 channels, that is 1, 2 and 3, and you can see on the screen there is not much activity. But when I start rotating this sensor, or when I start moving this sensor in the directions, and increasing the acceleration, you can clearly see an activity on the screen and the data values are changing. So the sensor is very much able to measure the acceleration in all the direction, and as I slow down the acceleration, you can see on the screen also there is not much activity happening. This all data is recorded digitally at 700 Hz with 16-bit resolution. So this is how we can use the accelerometer on human body for an activity recognition, which is also a very important task for any biomedical signal analysis. The most important lesson here is we should understand that the right number of channels deployed on the microcontroller, and those many channels also should be enabled on the OpenSignal software. Then only the communication will happen between this microcontroller and the device. So as you can see, when I turned off the microcontroller, the message came, device turned off. So as long as you want to measure the device, you can turn it on and record all the sensors. Similarly, we can use all other sensors, and at one time on human body, we can use 3 to 4 sensors maximum using this BioSignal Plug Kit. To measure the activity of human, we can tie it using the belt given in the kit. So using this belt, we can tie all the sensors on human body and record the values. Moving further, till now we discussed the BioSignal Plug Kit, which had 8 sensors, and I discussed all the 8 sensors and also demonstrated 2 sensors, that how Accelerometer was able to measure the data through OpenSignal app or OpenSignal tool, and also I have shown how the force response was being measured by the tool. Now moving ahead, for the smart health, we have another kit which is called MySignal Kit, and in this MySignal Kit, as you see, we can have more number of sensors. Those sensors which are not available with the BioSignal Plug Kit, we can use this MySignal Kit, which is nothing but an Arduino kit, and it has more than 8 channels where all the sensors can be deployed and data can be recorded using either an app or as well as the Arduino suite, where you can code in the C language and change the data rate, change the data receiving rate, change the data transmission rate, and you can change a lot of parameters using those codes and measure the data. This hardware kit is not only wired, but it also communicates through Bluetooth as well as Wi-Fi protocols. So at the back we have the Bluetooth chip as well as the Wi-Fi chip enabled in this, and to evaluate the data we deploy different sensors at the particular channel. The difference between the BioSignal Plug Kit and the MySignal Kit, one of the major difference is here the port is well described that only the ECG sensors can go only in this particular port, which was not the case with the BioSignal Plug Kit. But this kit has some more advantages, as you can deploy many number of sensors, which I'll be discussing. Different type of biomedical signals such as snore sensor, which is very important to understand the sleep pattern of a human being, which were not available with the BioSignal Plug Kit. So I will demonstrate some of the sensors. I will show how they work and how they measure. And for this kit, there, as I discussed before, you have an application as well as you have the Arduino suite where you can code in the C language. You have to burn the program and then see the output on the serial monitor. All of these codes, the example codes, are readily available on the internet free of cost. So you need to purchase or you need to have these sensors, and then using your basic programming skill you can measure the data. So moving ahead, as I mentioned, this particular kit has more number of sensors, and to name a few, we have here a weight measuring sensor, a snore measuring sensor, we have ECG, we have EMG, we have airflow sensor, we have a glucometer where we can monitor the sugar, basically for the diabetes patient. Also we can measure the blood pressure. We have the blood pressure sensor. Also we have a galvanic response sensor where we can measure the skin activity, the response of the skin. And we have a spirometer for the airflow coming out of the lungs of the body. We can also measure the temperature, pressure as well here. So just to demonstrate few of the wired sensor here, The first sensor, which is a very common sensor also, you can find it in most of the medical hospitals, is your SpO2 sensor. So this is an SpO2 sensor. In this sensor, it measures the oxygen supply, the amount of oxygen in your blood. So as you can see on this computer screen, it is both wired as well as Bluetooth enabled. So the sensor which we have is Bluetooth enabled, so I have to turn on the Bluetooth, and then as you can see the light is blinking here, the red color light. So I have to put my finger inside, and then I have to wait for the Bluetooth to connect to this hardware kit using the Arduino code, which will be burned on the system. For example, just to demonstrate you, this is one of the sensor platform for the Arduino, and here I have written the code to measure one of the sensors, which is blood pressure sensor here. So once I burn the code on this TFT and turn on the particular sensor, I can measure the values on the serial monitor of the device, which I can measure it here. So as I discussed, SpO2 sensor is basically used for the oxygen saturation, that is, it measures the pulse oximetry, and it is a non-invasive method. That means you need not to take out the blood sample, or you need not to pluck the samples from your blood. Moving on to the another sensor, the ECG sensor. So as I have discussed before, the ECG sensors measure the electrical conduction of the heart, the current that is generated through the pungent fibers in the heart, and to measure those we need an electrocardiogram. So just to show you here how does an electrocardiogram signal measure looks like, let me show this sensor to you. And as it is shown here, the sensor has 3 different leads, which I have mentioned before also. One is for the positive voltage, or for the plus, other is for the negative, and one is the neutral. So as discussed before, we will deploy these sensors on the chest as shown here also, and we will use surface electrode gel, which I shown before also with the MySignal Kit, and we will deploy it on the human body like this. So a positive goes here, negative on the left hand side, and the neutral on the right hand side, and then the right position to monitor the ECG is when somebody is if you want to monitor the right ECG, somebody should be lying down rather than standing or sitting. So we can use this as a wired sensor also, and as I discussed before, this wire cord should go to the right channel in the MySignal platform. So this is the MySignal platform, and as I can see here, the ECG part goes on to the channel number 3. So I can if I only connect with the channel number 3 for the ECG signal, then only I can monitor the ECG of a human body or of a person. So it is very, very important to understand that for MySignal Kit, the channel is fixed, which channel for which port we should deploy which sensor. So ECG will always go to the 3rd port of the MySignal Kit. Now moving ahead, once the program is burned on the Arduino kit, we can find out the ECG values. As you can see on the screen here, it is coming as in the just like we were seeing it before on the biosignal plugs as a waves. Here I can see it as the values as 1.93 volt, 1.65 volt, and we'll also find that it follows this pattern which I explained you before, the P, Q, R and S waves. So I would like to add one thing here, that we performed this activity for our research purpose, and we had recorded ECG signals of healthy person suffering from cardiac arrest, person suffering from different type of arrhythmia such as supraventricular arrhythmia and ventricular arrhythmia, and we deployed the deep learning algorithm. So if you remember the IoT structure, the first stage was the data sensing, which I am currently showing you that this is how the data is collected from the sensors, and the next stage, which is the communication, that is using some of the protocols that I have explained before, such as Bluetooth 4.0 or Zigbee or Wi-Fi, or for the longer range you can use LoRaWAN and 6FOX. So using these protocols, you transfer your sense data from the sensor to a storage device, or you can say the cloud. So we perform this activity, and there you do the computation, which is again a very the computation methodologies are very important and integral part of any IoT system. So the data sensing, the communication, and then the computation. So coming back to the ECG signal, we observed that for our research we found out by deploying a deep resonate on the ECG signal monitor, we were able to easily detect with 97% accuracy a healthy person and a non-healthy person. A person who has arrhythmia, which is the abrupt conduction of the current in the heart, and we were very much easily with the accuracy of 97% we were able to handle, and for that we used MySignal Kit and as well as the MySignal Kit to monitor the ECG signal of different type of person. So the point I want to emphasize here is that data collection plays a very important role for any IoT system. Now moving ahead with the sensors, as I have shown you on the TFT screen, you will see this sort of results for the PQRS wave for an ECG signal. This is how on the TFT you will find it out. And then moving ahead for our another sensor, which is the airflow sensors. Now the airflow sensor is a normal respiratory monitoring device which measures the respiration rate for the human body. Just to show you how this sensor looks like. For a normal person, the respiratory range for that this device can measure is from 0 to 60 ppm, and with the maximum intensity ranging from 0.3 volt to 0.3 volt. So as you can see, as I told you, they have to wear this particular flow sensor. So this is the sensor, a thin strip, if you can see that. There is a thin strip and this cord which will be connected to the cord, and this will be transmitted, the physical values will be transmitted to the MySignal Kit through the wire or Bluetooth enabled. This particular sensor is wired sensor, and as I mentioned before, this will go to only a particular sensor, that is the channel number 8 of the MySignal Kit. So just to show you how to wear this particular sensor, as I have shown you, you have to wear it like this. So this particular part has to be wear on the nose like this. So when you take the breath from the air, this particular metal strip measures that how much flow from the nasals is happening in the human body, which is ultimately connected to my MySignal hardware, and it monitors the respiration coming out of a human body. So as you can see in the figure, this particular metal strip has to touch the nasals, so that for the accurate measurement of the data, this is very important. And as I have told you, once you burn the code on the Arduino, you will find the voltage values for the airflow. For an example, here we have found it out as 2.43 volt, 2.51 volt for a normal person. So if you breathe heavily, this voltage value will automatically increase, which will indicate that person is either running or he is having some sort of abnormality. So this is a very important sensor for monitoring the lungs or the respiration of the human body. Moving ahead, this is the graph for a normal person. That's how the breathing measurement is happening. With time, the voltage values are fluctuating. So the next sensor which I want to discuss is a very popular sensor, which is the blood pressure. Blood pressure plays a very major role in cardiac as well as many heart related cardiac as well as the neuro related disease. Now you would have seen an analog BP measurement machine very popular in the doctor fraternity as well as in the hospitals. But for our research purpose, to collect the data from the blood pressure sensor, we use this MySignal's Bluetooth enabled as well as wired enabled blood pressure sensor. So in this blood pressure sensor, we can either use the wired signal as well as we can connect it through the Bluetooth. So as you can see in the diagram, one has to wear this, and as you know, the blood pressure sensor is measured from your hands. You have to tie it like this. So once you tie it, and you have to turn on the Bluetooth of the system. So I have turned on the Bluetooth, and you can see here that the blue light is blinking. Now once the blue light is blinking and the code for the blood pressure measurement is burnt on the Arduino, we can start seeing the values coming on the serial monitor. So you can see that for a normal human body, the blood pressure range is 120 by 80. So the systolic pressure is approximately 180 and the diastolic pressure is approximately 80. So this measures three things, this device. First is your diastolic. So in my case, you can see here that it is coming as 79. The systolic is 127 and the pulse rate is 72. So please remember the process that you have to connect the sensor for measurement through a protocol to your microcontroller, which will display the values by running the Arduino code in a MySignal Kit. So this is a very popular blood pressure sensor, which I just now demonstrated you. Moving further to another sensor which we have in this kit is the glucometer sensor. Now as we know, the diabetic patients are day by day increasing, and we have found out that the diabetes disease is very common across the age group. Even we have found it out with the kids, we have found it out with the infants, we have found it in adults as well as people ranging from 40 years to 60 years. So to measure it continuously, to measure it remotely, we use this glucometer which comes with this MySignal Kit, which is also Bluetooth enabled. So for this we need we need thin strips on which we have to prick we have to put a small prick on the finger, and we can take the blood out of the fingers and put it on the thin strips inside this glucometer and connect it through the wire to our MySignal Kit and burn the Arduino program, and we can find out the glucose values for a person. Also this is it displays the values also, so you can see on the screen also that how much sugar for a particular patient it is, and that is live. So you can currently see that using this glucometer which comes with MySignal Kit, that this much is the glucose level of a patient or a normal human being. So this is how, as I told you, you have to do a small prick in your hand to just and put the blood on the strip, and you will get the values. Also you can connect it through the hardcore wires so that it can be easily saved for the research purpose. The values can be saved on the cloud or on your workstation or server. So the values that are recorded from the glucometer can be seen on the Arduino using the Arduino tool, and we can see that for the patients we can have the glucose value here as 49, and for the next hour the next measurement is 54, the next measurement is 60. So we can monitor the glucose over a period of interval of time, and we can conclude that how is the glucose level of a human is changing. Now moving ahead with our next sensor, the next sensor that we have is temperature sensor. Now it is one of the most common sensor which can be easily deployed for measuring the temperature of human body or the room or any place. Here with the MySignal Kit, the advantage is we have Bluetooth enabled temperature sensor which we can use to transfer the data to a device which is at a small location from the measured location. So another important feature of this temperature sensor that comes with this kit is it has thin film strips which can be used to measure the sensors of a person that you can see here, that can be deployed on the temperature sensor, and the values can be digitally evaluated and transmitted to the device. So temperature sensor is a very common sensor that is used in healthcare. It also gives us an idea of how the other sensors are affecting the temperature. So one of the research area is when we use all sensor values, so which features are very important to predict the disease. That is a very important research area for a biomedical research with the biomedical sensors. Moving ahead, we can see also here that the temperature sensor can be applied on hands, on the toes, foot, also in the body, anywhere. So you can put it anywhere and you can see the temperature results coming on the Arduino. The next sensor that I want to explain you is a very important sensor, which is the EMG sensor. And as I have told you before that it is used for the electromyography. That is, we need the skin responses, we need the muscle responses from the human body. How the muscle is contracting, how the muscles are relaxing. Using those values we can predict the state of the person. What kind of work that particular human body is doing. Is it an active work? Is it a passive work? Is he sleeping? Is there no work happening? So these three electrodes are used and they are deployed on the human body. And as you can see in the picture, the muscles, on the muscles we use electrode gel here, and these gels are nothing but the surface data which monitor the activity, and you can see the plot coming that the intensity versus time plot for the muscle test is given. And we can have the contraction per minute values, and the range is 0 to 60 contraction per minute for this sensor. So you can see how this can be applied on the arms, it can be applied on the legs. So this image clearly tells that the ground is to be put on the elbow, and we can put the other two sensors on the different above the elbow and on the skin. So EMG plays a very important role for the activity recognition purpose, and EMG values are displayed on the Android device. And we can see that the values voltage are coming up as 2.17 volt, 2.19 volt, like that. Moving ahead, we can see that on the TFT screen also that how is the plot for the muscle contraction is happening. So this can be easily seen on our device, which is the MySignal Kit. We can see how it is responding live on the TFT screen, which is connected to your MySignal Kit. Moving ahead to our next sensor, and it is a very important sensor which is called spirometer. So spirometer basically measures the breadth of a person. That is it is a very common pulmonary function test, and which basically measures the functioning of the lungs, that how strong are your lungs, and for that we have to exhale and breathe heavily and see how strong our lungs are. So just to demonstrate it to you, I can this is how a spirometer looks. You can have a look at this, and we deploy the sensor in it, where we have to flow the air in this tube, as you can see in the image also, and in this it will measure the amount of air flowing per minute. So I'll demonstrate it for you, that you have to turn it on using the power button here, and once it is turned on, it is at the reset value. Then you have to flow, you have to exhale, and you can see that the value is coming as 226 because I have exhaled very heavily. Now just to demonstrate whether if I exhale slowly, how are the values changing, I will again exhale, and you can see the value degrades sharply from 226 to 96. So we can see that the person who has some lungs disease or who is asthmatic, definitely once the airflow we can measure for him, and we can predict that he is falling into which disease category. So as you can see in the images also, that this sensor measures the airflow. So moving ahead to our next sensor for the MySignal Kit, and before that you can see the values which I have shown on the screen also, and on the Arduino also. When you connect it to Arduino, you can see that the value, it is showing that spirometer is on, and it is measuring the values as 532 L per minute, 327 L per minute, 516 L per minute. Okay, so you can use your spirometer for for measuring the strongness or measuring the effectiveness of the lungs. Moving ahead with our next sensor, which is a very important sensor, that is the galvanic skin response sensor. Now in this sensor, just to show you how does it look like, you can see the image also, and on the live screen if I show you pardon me, it has two electrodes which are put on the surface of the skin of your hands, and they measure the conductance of the skin value. So what happens if you are in a state of shock? The conductance value sharply changes because the moisture level at the surface of your skin changes. So using this concept, it uses the conductance value of the surface of your skin. So I'll show you how you deploy it. So for example, you use on your skin, you just put it like this, and put the other electrode on the other finger like this, connect it to the MySignal Kit, and remember you have to put it on the right port. That is the most important part. You have to put, for every sensor you have to put it on the right port, otherwise the MySignal Kit will not respond. So putting it on the 2, 3, 4, 5, 7th number kit. So as you can see, it is in the image also, it is connected and it is measuring the skin conductance values. And when you run the Arduino code for this, the values which are coming for the resistance, conductance and the voltage, you can see it on the screen. So if you are in a state of shock, or if you are in a state of emotion, a happiness state or a sad state, these values will change. And using this we can actually monitor the brain state of a person, that in what sort of condition the person is going through. So this plays also a very important role for biomedical research, the galvanic skin response sensor. So moving ahead with our next sensor, and this sensor is the body positioning sensor, and probably this is the last sensor of this kit. So in this sensor we use basically the accelerometer using a belt. As you can see on your screen, we use a belt for measuring the acceleration, and basically using that accelerometer which is inside this belt, we can find out whether the person is lying down, he is lying left lateral, or he is lying right lateral, using the different acceleration values. So this is very important to continuously know in which posture the human body is, or the patient is lying in which posture. That is also very important when somebody is in any intensive care unit, or we need to know whether he is able to move in all the body postures or not. So this sensor plays a very major role. Moving ahead, you can see the values of the acceleration in the x-axis, z-axis and y-axis, and we use this value to predict the position. And as I have explained you before also, for our research work, we were able to predict with 99% accuracy using these sensors that whether the person is sitting, whether the person is sleeping, whether he is running, walking. These activities can be easily classified using some of the popular machine learning methods such as KNN with the proper distance function. So moving ahead to our next sensor, and this is another very interesting and important sensor. This is the snore sensor. So a very important common disease which is happening these days is the symptom of obstructive sleep apnea, that is called OSA. So as you can see on the live screen here, that this is the snore sensor. You can see it. We use this on the neck of the person, and once he is in the sleeping mode, we measure the snore values coming out of the nose or mouth of the person. So this is the snore measuring sensor, and as you can see on your screen, that this sensor is used for obstructive sleep apnea, and we have found out that in most of the sleep studies, snoring is detected with a microphone. So these study basically analyze the acoustic properties of the snoring, and you need the data with very high sampling rates. So that is why in the recent sleep studies we use the snoring sensor, which doesn't use these acoustic signals. Hence we don't need so much of data, and we can predict the disease for the patient who is suffering from OSA. So as you can see on your screen, this sensor, snore sensor, is weird like this picture. We have to put it on the neck, and once somebody is going to sleep, he has to press the button in his or her chest, and then using this earbud speaker, it will monitor the snore signals, and then we can monitor the snore values as in terms of voltage. As you can see, the snore value is coming as 1.76, 1.74, and further using our any machine learning model, it can be an HMM based, it can be GMM based, it can be KNN based. We can classify whether the person is having the disease issues or he is going through which sort of OSA disease. So this concludes our the sensors which are for the health here. So to conclude here, I would like to say that smart health needs smart sensor, and for smart sensor you have to make your sensors digital, and they should be able to transfer the data from measuring device to a cloud or to a server or to a PC. So these two important kits, which are BioSignal plugs and MySignal, these two are very important and efficient kits for biomedical monitoring of any human body and for the biomedical research. In the next few lectures, we will see the sensors which are related to smart city and smart agriculture. Thank you.